Can you see my screen?
Yes, sir. Yes, sir. You can continue.
Okay, thank you. Fine. So here I have three different presentation files today. But to start with, I'll use one and then I'll switch over to other in between itself. Okay. So here, for what you are currently seeing is the MEMS design challenges and opportunities that we have today as one of the research most popular research in the area of microelectronics. Okay, so here we'll see some basics of what MEMS is all about. Professor, are they aware of what MEMS is, or should I tell them what MEMS is all about?
You can take 2 minutes. You can tell that also. That is not a
Sure.
problem.
Okay, fine. Okay, so MEMS is basically a microelectromechanical system. It is a sensor or an actuator in the size of micrometers. Okay, so why MEMS? We will look into that, and what are all the MEMS devices that we have, and what are its advantages and disadvantages, and the complete design cycle. We will look into it. So first, we will see what MEMS device, sensor, or actuator is all about, and then we'll get into the challenging aspects of that. Okay, MEMS, as the word itself says, micro electromechanical systems. It's an integration of mechanical elements with sensors, actuators, and electronics. It is not just MEMS device alone cannot do all jobs. It has to work with electronic circuits as well. Uh, so it is done on a common silicon substrate through microfabrication technology. Okay, and here it is the specialty where it lies with MEMS sensors to other compared to other sensors is the mechanical motion that it involves here. Okay, so there are IR sensors, there are thermal sensors, there are chemical sensors. So those are also our sensors, but here the specialty here is it has an actuator, it has a physical movement. Okay, so until 1969, silicon was used only for sensing applications or for IC technology with a CMOS or BiCMOS process. Later, it was realized that it can also be a mechanical element. That's when the word called micro machining came into picture. Okay, the word micro machining means silicon material. Using a silicon material, we are creating a sensor which has a physical movement. Okay, so and it's an emerging technology with combining multiple physics disciplines, and its range is in the scale of 1 micrometer to 1 millimeter. So that's the scale range that we have. Okay, and why MEMS? It is small in size and low power consumption, lightweight, low cost, portability wise, and once it is produced, the repetition of the technology makes the cost very low. So that's why it is reproducing manufacturing cost comes down, and excellent control of material purity because it happens in the clean room condition where the IC also is being fabricated. And it's we can do these things with precise control of dimensions, and it integrates with multiple functions like sensors, actuators, and electronics. So it's a advantageous uh, technology for building sensing applications. Okay, so the current successful MEMS devices that we have in the market is one is the accelerometer, and one is the gyroscope, and another is the microphone. Okay, the accelerometer as such, you can see the two electrodes, one is in orange color and one is in green color. So the orange entity keeps moving when there is a vibration that is seen, and that vibration is the device vibration is tuned to specific value of frequency. So when it observes that frequency, it vibrates. So there is a small potential between the two electrodes, and that changes the capacitance between them. The rate of change of capacitance is measured, and that's where we have the accelerometer device start functioning. And there is a small change between an accelerometer and a gyroscope. The gyroscope part is in the case of accelerometer, so the device works only when there is vibration. But whereas in gyroscope, the device is always in the motion, and when there is a vibration in a specific direction, meaning the reference axis, if the vibration has a different reference axis, then the sensing part comes into picture. So there is a small difference between a gyroscope and an accelerometer. So in a gyroscope, we can measure the Coriolis force. In accelerometer, we cannot measure Coriolis force. So that's the only difference between the two. And MEMS microphone, as such, microphone is quite popular, quite old device. And MEMS microphone has already come into picture in the last 2 years in the consumer electronics. The gyroscope is used mostly in the aerospace, and now it is already there in the automobile also. The gyroscope is the person who decides whether the airbag should pop out or not. Okay, so that's where we have the gyroscopes. And accelerometer and gyroscope have also found its place in mobile phones also. We call it as IMU, inertial MEMS unit. Inertial MEMS unit is a combination of accelerometer, gyroscope, and magnetometer. It's called IMU, inertial MEMS unit. So that is there in our smartphones as also. Okay, so these are some specifics about the devices, and in case if it has to work, then we have different methods to actuate. So one is the thermal forces, another is the electrostatic force, magnetic, hydraulic force, and piezoelectric crystals and shape memory alloys. So different methods of actuations are available. Okay, so here with these basics, I'll take you to another file where we'll see what gyroscope is all about. Okay, so this is a device of a gyroscope model. So gyroscope is a device which measures angular velocity. Okay, so there are different types of gyroscope. One is called the tuning fork gyroscope, another is called the rotatory gyroscope. Okay, so vibratory gyroscope. So there are different types of gyroscopes. So here, this is a tuning fork gyroscope, and this design is taken from a paper which has been published by Georgia Tech. Okay, so we'll see how this is being designed in the software. Okay, so and how the simulation can be done. Okay, so the element-based modeling design. So what we do is there are two different types of approaches. One is the top-down approach. That's what we will see. And we drag and drop these elements, connect them like a circuit, and then we create the model. So this is what the gyroscope model looks like while designing. Okay, so we connect these elements like beams and plates and comb drives. Okay, and then we can do the top down flow of the design. Okay, so here we can set the beam properties, the beam materials, its dimensions can be set, and this is what we have this as a gyroscope with respect to top down approach of design. Okay, we have bottom up approach also. We'll see that later. Okay, so here this is what I call it as a top down approach. So you can see that this model is done using this elements. Okay, so here it's a vibrating element. Naturally, any vibrating element, we see its natural frequency. So natural frequency meaning any device in the world has its own natural frequency value. Okay, so we want to see the natural frequency value because we need to see the operating condition of it. In case if the gyroscope has to work at 200 kilohertz, we will have to see at what will be the natural frequency of the device. Okay, remember that the device is not operated at natural frequency, it is always operated at close to natural frequency. Okay, so it is not operated in natural frequency. So for that we do a sweep over analysis. So here this is an example where we have a 12K to 18K sweep over and we see a resonance plot. Okay, so all these MEMS devices, though these devices are mechanically or mechanical devices, the functionality can always be correlated to the electronic circuits. So what we have it as a acceptor circuit or a series resonance, or simply we call it. So those circuits, the response is the same here. So it vibrates to a particular frequency. The maximum vibration is seen to a particular frequency. Okay, and then we in the y direction we have 16.4 kilohertz, so we can check that, and then we can get the results in 3D model. So here ambient condition also matters. What is ambient condition? Most of our simulation what we do are all ideal conditions generally. Okay, we don't, sometimes we don't consider at what temperature or what will be the temperature effects on the working of the device. So those things can be estimated here. Okay, and we have temperature, pressure, the viscosity, the lambda, film coefficient. So these are the things that are at the ambient condition: the temperature at which we are operating, the pressure, the viscosity of the fluid, is what we see. And you can see that its response changes with different pressure conditions also. Okay, so you can see here at different pressure conditions, the resonant frequency changes. Okay, so the resonant frequency changes here. So what we are seeing right now is the change in resonant frequency for different pressure values. So atmospheric value, a little higher than that, and much higher than that. So three pressure conditions. Okay, so the same thing, we start with this. So I'll directly skip on to the results part of it. So we have the vibration that starts. So you can see any vibrations, the amplitudes start small. So we see this amplitude also starts small, and this is where we can see how long it takes to achieve the maximum vibration. So a transient simulation helps us to understand this. Okay, and we also measure the Coriolis force. Okay, so the Coriolis force is something like an angular velocity. So we apply Coriolis force and then get the response. So when the device is functioning, say I say that the device is functioning, so then what does it mean? It means that the device is always vibrating to a particular frequency value always, and when there is a change in the reference axis of the device, then it senses the change in the reference axis, and that's when the gyroscope comes into picture. Okay, so here you can think of something like a vibratory a device which is in the vibration in x-axis. Okay, and between the x-axis and z-axis there is a small change in capacitance. There is a fixed value of capacitance, as there is no change in the gap between the two. Now suddenly, if my reference axis is in y direction, then my device, which is vibrating exactly horizontal, changes its direction. So that's when the distance between the two elements in the z direction also changes. So for which there is a change in capacitance. So that capacitance change is seen. So later there is a video from Bosch. So probably you will be able to understand what I'm trying to tell you in that video. Okay. So here we have this quadrature effect. The quadrature effect meaning while fabricating there are few imperfections that can be seen. So those imperfections can be simulated well ahead of fabricating the device. So and then we can estimate what will be the worst case performance of the device, because simulation output is always ideal condition and we don't get the same response when we fabricate the device. Okay. So another method is the top-down approach. So one method is top-down approach, what you saw using the element-based modeling. And now we are seeing the bottom-up approach where we create the layout file and then we can do the FEM simulation. Okay, so here you can see that we set all the material parameters. All these devices are silicon based, so it is having its mechanical properties and electrical properties as well. We set them and then we set the simulation and then we get the response, the mode 1, mode 2 and mode 3 and different modes of vibrations. So this is what we have as different modes of vibration. Okay, so we do the static simulation, that is one input, one output. The frequency response, meaning the natural frequency is estimated, and dynamic simulation is to understand how fast my device responds. Okay, so that's what we will be seeing here. Okay, so we do the static simulation and get the maximum displacement. So why we do the static simulation is because we need to see for the vibration that we apply, what will be the maximum displacement between the two electrodes. So here you can see that there are comb structures. Okay, so the comb structure here, so this is the comb structure, what you are seeing. So this comb structure has two different potentials. So when there is a vibration, one goes into the other and naturally the overlapping area increases. So hence there is a change in capacitance. Hence we need to see what will be the maximum displacement so that the overlapping area increases, so that the sensitivity also increases. Okay, we do the dynamic analysis by applying a Coriolis force and gets its response in different directions. Okay, so here we also do macro model simulation where we calculate the model contribution, strain energy associated with each modes of vibration, and the mutual capacitance between the two, and then we convert this into a HDL file. The reason we are trying to do this simulation called macro model is because that the MEMS device as such have to be integrated with other electronic components. Okay, in case if the electronic circuits do not understand the input signal properly, then what's the use? So what we have is we need to create these circuits in to read the signals of these MEMS devices. So that's why we have the what we call it as the reduced ordered model simulation we do, and then we connect them with the other EDA tools for IC simulation. Okay, so here what we are seeing is a Lagrangian model. So as such, we can compare the FEM simulation and also the simulation of the Lagrangian model, so that we have a benchmark in the device that we are trying to build. Okay, so I'll directly go to this result. So here, when the device is functioning, meaning it is vibrating in particular direction, then it's called as the drive mode. Okay, so in the drive mode with element based modeling, we have 15.6 kilohertz. With thermoelectromechanical FEM simulation, we have 15.6 kilohertz, and macro model simulation also we have 15.6 simulation, 15.6 kilohertz. Okay, and DC displacement, meaning that displacement for which the load that is applied, we have 0.22 micrometer, and in FEM we have 0.21 and 0.22. So this simulation part is taken to other EDA tools by doing this macro model simulation. I'll directly take you there. So this is where we can convert this MEMS device into equivalent Verilog A file. You can also convert it into a MATLAB file, Simulink, MATLAB, Tanner, PSpice, HSpice, VHDL files, and then connect them in other EDA tools. So these slides, what you are seeing now is the slide of uh, a Cadence software. Okay, so we can integrate MEMS device with other EDA tools for interfacing the circuits and also the MEMS device. Okay, so we have this procedure here. Okay, so what we see, this component, this element is a gyroscope model, which is a black box kind of a model in Cadence tool, and that is being interfaced with other components, electronic components, to read those signals. Okay, so we have verified these simulations, and most of these simulations have produced the same results even in Cadence. So what you see here is the Cadence simulation results. So we have the similar results coming from Cadence and IntelliSuite in both the softwares. Okay, so here we do the frequency simulation and then the model parameters. So the distance between the two peaks. Okay, so here we have the mode 1 peak, or else I would say it this way: the resonance frequency of mode 1 and the resonance frequency of mode 2. Okay, the difference between the two is the band gap or the bandwidth of the gyroscope. Okay, and it is always very small between the two peaks, mode 1 and mode 2. Okay, so this was on the gyroscope part of it. Another model what I have is the energy harvesting device, that is a piezoelectric based energy harvesting device. So one more MEMS device as such. Okay, so what we see is, in this case, I have picked it up, this design, from one of the recent paper. Okay, I'll show you that, show you which paper it is. So with piezoelectric material as such, there is a distribution of charge carriers on either sides in the material. So when there is a voltage, when there is a force that is applied, there is an imbalance in this charge carriers, and that's when it produces the potential. Okay, the other side of it is, if we apply potential, due to the imbalance in the charge carriers in the material, it starts deflecting. Okay, so a piezoelectric material is always sandwiched between two metal layers. Okay, so that's what we have. So here, the motivation here to build any energy based energy harvesting based device is to capture the vibrations around us and then convert them into electrical energy. Okay, so here, this is the recent paper which you are seeing on the corner, right corner. So 2019 paper. So this is where the model looks like. So this is the model image picked up from this paper. And here it has two elements. One is the top plate and one is the bottom plate. the architecture goes like this. Okay, so one of the top plate and another is the bottom plate. The top plate has a resonant frequency of 1 kilohertz. The bottom plate has somewhere around 50 hertz. So whenever there is a vibration that comes up to it close to its resonance value, then it starts vibrating, and then due to the vibration, the charge carriers are captured to generate the electrical energy. Okay, so this is the functionality of it. Whenever there is a vibration, the fellow which is at the bottom goes and hits on the top, and that's when the charge is produced. So a piezoelectric material is put on the top of this blue entity here. Okay, this is the functionality of the piezoelectric crystal in this paper. Okay, so here the same simulation, the static, frequency and dynamic simulations is possible. Okay, so here you can see that the potential generated, frequency versus potential. So whenever there is a change in acceleration, there is a change in potential generated. Okay, so here in this case, whenever there is maximum acceleration 1.5 g, 0.35, close to 0.35 volts, that is 350 millivolts of uh, uh, potential is generated. Okay, so same thing with respect to time. How long does it take to generate that potential? So we can see that here with respect to the resonance. So each one of the plate has piezoelectric material put on that. So one plate captures the vibration in the range of 1 kilohertz, another plate captures the vibration which are less than 100 hertz, and both of them contribute to producing the charge. Okay, so here these are some of the videos, and that's where it I think the displacements are quite small here. Okay, so we have two devices that we saw, and in case of any device that you want to create, the only methodology that is available is do the static simulation and do the dynamic frequency simulation, and then do the dynamic simulation. So any device, irrespective of any electronic component that we do design, we see the static response, we see the dynamic response, and we see the frequency response also. The same thing goes here as well. Okay, so I come back to my presentation one here. So this presentation makes it very generic for you. In any device that you are planning to design, any MEMS device that you want to design, how IntelliSuite can be very useful both in your research and both in the both in the research and in the process of optimizing your device. Okay, I'll showcase you all of these things here. Okay, when it comes to this design, we'll have to see whether it is a mechanical device, whether it's a thermal device, or whether it's an electrical device. If it is a mechanical device like gyroscope, then we will see what is the functionality of it. Functionality meaning whenever there is a vibration that is applied, then the mechanical there is a electrical signal that it is changing. The electrical signal, is it a potential? If it is potential, then a piezoelectric material is used. If it is not potential, then what is the signal that we are capturing? Another common signal that we have is the change in capacitance. If the change in capacitance comes into picture, then it becomes electrical simulation also. So that's when it becomes electromechanical simulation. Okay, so similarly, if we are trying to build any device which are thermal based, so whether it is thermal only, or is it heating due to electrical signal, or due to change in heat, there is a change in current that is happening. So that can also be simulated. So then that's when we have thermal mechanical, thermal simulations or thermal electrical simulation. Okay, so similarly, you can combine this mechanical and thermal with electrical also. Okay. So here as such, we have a design requirement and we have a basic design and we have the optimization process. And how do we address this in the software is by providing that software with the, by feeding this with the appropriate design. So we can do the 3D CAD model and then we do the thermo-electromechanical simulation TEM, and then we do the reduced ordered modeling simulation, and then we do the system model extraction, and then we do the system level integration. Okay, so this is the whole cycle of the whole process of how to achieve the device. Okay, and then we create the layout of the device, and then we optimize the process, and then we do fabricate the device, and we do the testing of the device. Okay, so this is a hierarchical model of how the design starts from a CAD tool and then it goes for testing the fabricated device. So at every layer, at every stage, there are lots of challenges. So we will see what are all those challenges. Okay, in terms of design, I'll start with the bottommost in the pyramid, the design model. So the design model in this case, so we have a 3D model, we need to optimize them. So naturally, any device have to be optimized. It has to be in the process of optimization. What are all the changes that we do? We change a lot of materials, we change a lot of dimensions. In that process, we do a lot of designs. Okay, in the design, it takes a lot of time to do multiple designs. Hence, we have a tool called parametric designer, where you tell the software that this is what I need to do, and this is what I need to do, meaning that I need to see the response of the device for a geometry of 1 micrometer to 10 micrometer in the increment of 1. So tell the software, please do it for me and show me the result. So it can do the simulation for you, wherein you don't have to redesign the structure. Okay, so you give the basic model and then you can increment the dimensions or decrement the dimensions based on the requirement. So that's where the challenge of the design optimization comes into picture. Okay, another is the system level simulation, where once we have the design model, then we need to integrate this with other EDA tools or electronic components in simple. Okay, the system level simulation, element based modeling, MEMS plus ROIC, ROIC meaning readout integrated circuit, and then we have the thermal system model extraction, and then we have the reduced ordered modeling and MEMS plus EDA. Okay, and once the MEMS design optimization is done, then we have the electronic component, that is the ASIC, application specific IC, or the circuit, electronic circuit is designed, and both of them have to be fabricated. So if most of you are aware of IC simulation tool like Cadence or Synopsys or Microwind, so the end goal is to create a layout, okay, of the circuit. The similar thing happens here also. So here we have the MEMS device, the layout is created, and we have the system level simulation where we create the IC and the layout is created. The only difference between the two is the MEMS device is in the scale of 1 micrometer, okay, or in the micrometer scale, but whereas the circuit is in the nanometer scale. So both cannot be fabricated together. So what they do, they separately fabricate both of them and then place next to each other and then connect them like a wire bond, and then they encapsulate with standard packaging, IC packaging methods. So here in that process, we need to have the process optimization both for nanoelectronic component, that is the ASIC, application specific IC, and also for the MEMS device. So the process optimization, we create the layout. So layout is very much important, whether it is IC or the MEMS, because both of them adopt a CMOS process. Okay, and then we have the recipe, the process simulation, and then we calibrate them. So process simulation meaning what are all the challenges that can be seen or predict, that can be seen during fabrication can be predicted here, so that the process can be optimized well uh, before, so that less time, less iteration, so less cost is involved in fabricating the device. Okay. So the challenge here is the 3D CAD model we prepare, and then we have the FEM simulation, and then we the parameters that are involved, the dimensional parameters and the material parameters that we have. So what's the solution for it is we can parameterize the structure. When we parameterize the structure, meaning that we tell the software to redesign this device and show me the response of this device for various dimensions. Okay, software does the job and gives us a graph for these dimensions. So these are the possible outputs that we can get. So parameterize the input variables, that is the input load, whether it is pressure or force or electrostatic force or mechanical force or acceleration or temperature or current. So whatever is the input that we want to give, so we can parameterize them as well. And then we do the system model extraction, and then we do the reduced ordered modeling. Okay. So this is the standard approach that any MEMS tool does. So we have something additional. What is that additional is we have top-down approach, that is the element-based modeling. Element-based modeling is more of a lumped model simulation where you can also parameterize the structural and also you can parameterize the input variables. And then we can compare the results of FEM and element-based model. Okay. So another third challenge that we have is the process. So we create a layout, we have the process recipe and process integration. So we need to perform some checks, something like design rule check. What is design rule check is, say you have designed some device where you want to fabricate. Where will you fabricate? We'll look for some foundry. We will share the design and they will say we cannot fabricate this, because every foundry has their own design rules. So our design should be well within the design rules of any foundry. Okay, so that's what we have to keep in mind if we are having a plan to fabricate the device. Okay, the process verification can be done, and the design rule check with a foundry that you want to fabricate, you can get the design rules, create a template, and then we can run the template on the file, and the software tells us where all the deviations that are there which are not meeting the design rules of the foundry where you want to fabricate the device. Okay, so we need to balance the two worlds here. One is the device response while during the fabrication, and one is the simulation response during the fabrication, during the FEM simulation. So we will see how both can be balanced. Okay, so fast field multiphysics is basically a simulation method where it combines different physics problems and then we consider them to simulate any device. Okay. Okay. So some of the examples that we have here is the Seebeck potential can be measured, nonlinear device can be simulated. So here, this is a micromirror, dual axis micromirror device, and we have a cantilever beam which has 3 different types of contacts, 3 contact pads, and we have a resonator where a resonator can also be connected to electronic circuit to read the signals that are coming from the resonator. And finally, we can do the packaging simulation also. On the right side, what you see is a thermal packaging simulation of MEMS gyroscope. Okay, so we have the fluidics simulation. Don't stress upon this one because fluid simulation is quite complex, and most of these things are to be experimented. Some of the things can be simulated well ahead of a simulation, but as such, you can take a look at these methods of simulating something like the electrowetting, electrochemistry, the micromixing, the dielectrophoresis, and micro pumps that we can build. So some of these simulations which are in the scale of micrometers can be simulated, but the major problem where we see in terms of flow simulation is the device is too lengthier. It will be 1 centimeter, and the size of the device, sorry, the size of the microchannel will be in micrometers. Okay, if that is the case, then it's two different things. Like the length of the device goes so high that the software cannot handle some of these dimensions. So we need to plan accordingly to if we at all want to simulate the flow simulation, the microfluidic simulation. Okay, so what benefits do we get here? The benefits that we have with our FEM simulation, with our element-based modeling simulations. So here we have the 2D and a 3D layout that we can create. 3D models can be created, and we can use a module called as TEM preprocessor to set the simulation very fast, because these are CAD models. If the performance of the PC is low, then the response time when we want to feed the inputs will be too high. Okay, so that's when we have the preprocessor, and it saves a lot of time because we tell the software to do the design by yourself, and we feed only the basic design for it. Okay, and then we do the post processing job, and then to see the results, and we also do the macro model simulation where we verify the FEM simulation with a Lagrangian based model output. Okay, so when we have two outputs, both can be compared well within the software. Okay, as a researcher, comparison with two things is always a good method to benchmark the model. Okay, so we have the element based modeling. So drag and drop of these elements, we can do the MEMS simulation as well, along with connecting them with the electrical circuit. So we also get the 3D output. Okay, and then we have the layout creation that can be done with the element based model itself, because we don't have to redesign every time we want to create them. Okay, so the element based modeling, the layout can be created, the process can be defined, and then the simulation can go ahead. Okay, so what are the benefits that we have here is the schematic based design. We have a hierarchical model, so we save a lot of time. Okay, in the element based modeling, 100 to 1,000 times faster than FEM models. And we have design, exploration, optimization. We can also tell here that please do the parametric simulation for these dimensions. So you can parameterize the input load. You can also parameterize the structural. Okay. Yeah. So once we have the benchmark of both the problems, okay, or both the devices, then we try to fabricate them. So we have the 4 different steps of microfabrication. One is the deposition, another is lithography, and another is etching, and finally the bonding. Okay, so these are the major 4 steps with different masks and different materials contribute microfabrication. So the summary of it goes like this. Materials is being deposited, we keep the mask on this, and then we do the etching, and then finally the etched output is bonded, whether it is silicon-silicon bond or silicon pyrex bond or glass silicon. So there are different bonding techniques. Okay, so as a researcher, how IntelliSuite can be used in MEMS research. So let's look into some of the research opportunities that we have in case in MEMS simulation, in case if we choose IntelliSuite software. Okay, so as I mentioned earlier, that if we are trying to do a FEM simulation, we have parameterize the structural. It saves a lot of time, and in addition to that, we get more information by parameterizing the device. We get more information about the functionality of the device if it is parameterized in all the 3 directions. How the thickness respond, how the response of the device changes with respect to thickness, with respect to width, with respect to length of the device can be parameterized in the software. Another parametric as an input variable, and then we convert this to a system model extraction, then we do a reduced ordered modeling simulation. So let's see how the parametric simulation works. Okay, so let's see this. So as an accelerometer, as an example, it is a vibrating element. The green entity, what you see, is called as the proof mass, and the 4 beams which are connected are the hinges, are the beams that are holding the proof mass, and on all 4 sides it is fixed. So now I want to see what will be the change in natural frequency of the device with change in thickness or change in length. Okay, so with respect to change in length, you can see that the frequency response changes. Okay, so that's where we don't have to redesign every time. We can tell the software that you can do these parametric changes, and then you can give us the output. So here we have the change in displacement versus parametric load. So we can even parameterize the input variable. The similar thing with respect to comb structure. So this is what the MEMS comb is. So we want to see what happens if the overlapping area increases. So what will be the change in capacitance? So here we can get that output, the change in capacitance with overlapping electrodes. If the electrodes are less overlapped, then there is a reduction in capacitance. So we don't have to redesign every time. We can tell the software to do all of these jobs. In terms of electric energy harvesting device, which I mentioned of the piezoelectric beam, what will be the potential generated if the thickness increases? Because with respect to piezoelectric material as such, what we know is it is more sensitive if the thickness of the piezoelectric material increases. Okay, so how it improves is what we can see. These FEM simulations are quite standard with any MEMS software, but what makes us more unique or more reliable is the system model extraction. So the system model extraction, meaning that the device can be can you hear me?
Yeah, sir. Hello.
Okay, yeah, there was a I think my PC went on mute for a second. Okay.
Go.
Okay, fine. So here, as such, the device can be extracted to convert this into a HDL file. So HDL file, when it is created, I can convert the signals that are coming from these MEMS devices to a signal conditioning system. I want to read these signals or process these signals. These things are not possible in FEM simulation. Okay, so that's when we reduced ordered modeling helps us. So reduced ordered modeling as such helps us in building the equivalent Lagrangian model. One advantage is, this is one advantage, and another advantage is it will allow us to integrate this with other components like signal conditioning systems if we are trying to build, which is not possible in FEM simulation. Okay, so what will be the outcome of it? Okay, as a researcher, what I can expect? So I can expect the FEM simulation, and we can get the system model extraction plus reduced ordered modeling, the Lagrangian model, and compare the results of Lagrangian model and FEM simulation as well. So by parameterizing the structure and also the input load, we can completely understand the behavior of the device. Okay, and clarity on the device, we can target any application. Okay, so these are some of the outcomes that we can get with respect to FEM simulation, okay, using IntelliSwift software. So another way of design and also the simulation is the top-down approach, that is element-based modeling. Okay, not all device need be not all MEMS device need to be simulated in 3D model. So element-based modeling also helps us. So here the element-based modeling, what I'm talking is something like this. So we have beams, drag and drop them, connect them like a circuit. The same beams can be used to create different structures. So you can see a serpentine beam is connected to a element, a plate element. We have beams which are converted into a serpentine structure, so that a cantilever beam is connected via the serpentine flexure. Okay, and we have the beams and the plates, a single cantilever beam connected to a plate, a cantilever beam, the same plates and beams can be used to make a resonator, and the same beams and plates can be used to make a gyroscope. Okay, the same components connected in different configurations generates the required MEMS device. So this is another way of designing, that is, this is called as the top-down approach. Okay, so here also we can parameterize the structural. You can see that there is a change in response with respect to thickness. So the maximum, the accelerometer device, what you are seeing here on the right side, if the thickness increases, how the resonant frequency comes down is what you are seeing. Okay, and the same ambient conditions, in case if the pressure around it increases, how the resonant frequency can come down is what we can see. So what I'm trying to tell you is the element-based models can also be parameterized both in terms of dimensions and both and another is in terms of input load. The ambient conditions can also be set. Okay, so 2D and a 3D graphs can be plotted. So what is the outcome that we get is the simulation model. So we have the parametric simulation output that we can get from the FEM models, static, frequency, and dynamic simulations, and the results are generally ideal unless otherwise. Meaning to say that the device output are always ideal conditions in FEM, because the input does not consider any damping effects unless we feed in. Okay, but whereas in element-based modeling, we don't have that problem because it can be simulated with different ambient conditions. Meaning to say that any device have a damping effect only because the ambient conditions around it. So for MEMS device, the fellow which acts as a damper is the air below the device. Okay, so air below the device is a fluid in nature. Okay, it's a compressible fluid, so it has molecules, it has mean free path. So based on that, what will be the damping effect that can be seen can be observed in element based modeling, but these effects have to be externally given with some assumptions in FEM models. I mean, this is what we have. Okay, so it's always better to set the ambient condition rather than giving some approximate zeta value. Zeta meaning the damping coefficient. Okay. Okay. So assume that you are at a stage where you want to fabricate the device. Okay. So how do we start? So if you want to fabricate the device and if you are aware of the fabrication methods, then you can directly coordinate with the fabrication engineer or the process engineer. But sometimes we don't know how to fabricate the device. So that's when the standard templates comes into picture. Like the way we learn programming by executing some of the well-established codes, similarly, we have these templates available for MEMS processes also. Okay, so we have these MEMS processes called multi-user MEMS process called as MUMS. Okay, so we have different MUMS process, polymums, SOI MUMS, Scream, Summit. So these are the standard MUMS processes. Only the layout changes. Okay, and the fabrication method remains same. The advantage of choosing this one is low cost fabrication methods. Okay, whereas in generally speaking, as beginners we say that go for MUMS process, but industry wise if we look at, then it is always a custom made process flow. Okay, so that's why the MEMS device, the first iteration of the MEMS device is always expensive, only because it has to be fabricated fresh with a custom made process for the device. Okay, so once the process is established, then only the repetition of fabrication, so that's when the device cost also comes down. This is the same reason that we can get the lab components of different IC less than 10 rupees, because the process is already set way back few decades before, so that it is just a repetition. Okay, it's more of a repeating the same process again and again. So that repeatability, when it comes, the price always comes down. Okay, we have an extensive material database and we have the process traveler as well. So these are the standard MUMS processes available. Okay, the custom made process goes like this. Okay, so this is the process. What you are seeing is from it's from a paper which was published from Stanford University. So this example, what you are seeing on the right side, is an example of a nano hole array. So nano hole array is a device. Technically it is called like that, but when it comes to application, it is used for as a waveguide. It can be used as 1D or a 2D crystallographic application. So here the device is called, one second, I don't, photonic crystal cavity. Yeah, so the photonic crystal cavity, or as a photonic crystal waveguide. So like the way we have filters, here these holes, what you are seeing, I repeat the video again. So these holes, what we are creating, the nano holes that we are creating, can guide the light in particular direction. It can guide the light of certain wavelength in particular direction. So it is more like a waveguide. Oh, sorry, it's yeah, of course, yeah, it's a waveguide. So photonic crystal waveguide. So it can be used as a photonic crystal cavity. It can be used as photonic crystal uh, waveguide, okay, as a filter. So you can give different names to it. So, but functionality wise, it remains the same. So in simple, it's also called as nano hole array because it's an array of small holes. Okay, so the custom process can be designed and simulated well. So these simulation are not just graphical representation. So here these are real-time process simulation. Real-time meaning whatever you get at the fabrication, when you fabricate, the same profile can be predicted here so that you can plan your mask layouts accordingly. Okay, so this process can be exported to PowerPoint presentation. So I'll show you this. The software can create a PowerPoint slide. So how this photonic crystal cavity was done, we have taken a substrate, deposit SiO2, PR material, we do the etching, we protect this layer with oxide, again we do etching, again we protect, again we etch. So that's where we created the process for this. So here the software can generate the PPT file. You don't have to worry about that. Okay, so as a researcher, this saves at least 2 days for you. Okay, so the creating a PPT for a process simulation is extremely difficult. Okay, okay. So here we have the export to Excel. So I'll skip that part of it. So that the Excel file is required for the process engineer. Okay. So here we have what we call it as the bulk micromachining. A crystal plane of a silicon is standard. What we see is 100, 110, and 111. But there are other plane orientations also, which are complex in nature. So why these things are required is because if we look at the atomistic structure of these devices, sorry, so it is a pattern of arrangements of different atoms with covalent bonds in different directions. That's what determines orientation of any crystalline material. So silicon as such, we have quartz. So in silicon, we have 100, 110, 111 different orientations. So we get different orientations. So here, how does it matter? So in when we are trying to do the design, say we have developed a design with silicon material, we don't know, we just say that it's a silicon based device, or my accelerometer is silicon based. But as a process engineer, when here he hears that, he will ask one more question, that whether it is 110 or 11100 orientation. That's when as a design engineer I get confused. How does it make a difference? Okay, because it makes a difference because you can see the same mask layout, the same mask layout, same type of sorry, the same chemical what we are trying to etch, KOH, that is potassium hydroxide, produces different shapes. You can see the one which is in the first has a different shape outcome, the middle one has a different shape, and the third one has a different shape outcome. Okay, so that's when we need to see what should be the silicon material for us to design the required device. Okay, okay. So similarly, we have another chemical called as TMAH, tetramethyl ammonium hydroxide. Okay, so these things, and tetramethyl ammonium hydroxide with 150 minutes of etching on 100 and 110, and yeah, 111 is different because etching 111 is extremely difficult, so naturally it requires more time. So here what you see, the same chemical, same minutes of etching, but the profile is completely different. Okay, so we need to be aware of all of these things before we get into designing MEMS device. I'm not scaring you people that you need to know so many things. If you're restricting yourself to creating a MEMS device with only the multiphysics as simulation, you need not worry about all of these things. But as such, when you are planning to fabricate the device, so these things are much important. Another way of saying is, if you are more interested in silicon processes, then you need this tool to understand your silicon process much better. So you can do a micro and nano fabrication simulation also here. Okay, so similarly, we have the AT cut and Z cut for quartz material. So like the way we have 110, 111, and 100 material, here we have AT cut and Z cut for quartz. Okay, the same mask, the orientation or the plane outcome is different. So if we take the mask layout to be like this, then if we are doing if we do a isotropic etching, the profile goes like this. The profile generated is like this. For the same conditions, if we do an anisotropic etching, then the profile is V-shaped profile. If we do a dry etching, it's a rectangular shape. The side walls are all straight. Okay, so different orientations. So these are all directional etching. Okay, so these are all directional etching because it is these shapes are based on the pattern of arrangement of these atoms in a particular pattern. I would say that way. Okay, so plasma etching is more of a dry etching process where we use gases. If we take a square layout and then we etch the silicon with KOH, and this is the shape that we can achieve. The same square layout, if we do the etching for the same condition but add something called as isopropylene alcohol, then we get this profile. Okay, with the TMAH alone, we get this profile. So you can see the top one, KOH and TMAH. The profile is completely different. So okay, so the KOH and TMAH, two etchants are there. The advantage of using TMAH is there is small limitation with KOH. At certain dimensions, it leaves some charge carriers during etching. So when it leaves some charge carriers during etching process, then these are electrostatic, these are electrical devices or electronic components where charge cannot be left arbitrary wherever we want to. So that leads to a lot of other problem, ESD, electrostatic discharge, and other problems. Okay, so that's why a TMAH is used on a safer phase. So here we add a triton, which is a surfactant, in a TMH with some volume, and then we get this profile. Okay. So what I'm trying to tell you is, if you are planning to fabricate your device, or if you are a process engineer, or if you are interested in process um, of these silicon quads, so how the profile is generated can be well be predicted. Okay, so for that I'll show you one interesting example. If we have to have an octagon shape on a silicon material, as a general MEMS person, what I think is octagon shape can be created by octagon shape of mask. That need not be. So here you can see that plus mask plus the shape mask can also be used to create the octagon shape. Okay, so if you are a process engineer working in IISc, working in IIT Bombay, working in SCL, Ilani, Rajasthan, or any other small fabs that you have, if you are trying to fabricate, please be aware of all of these things and if you want to see or reduce a lot of time in your clean room, then please simulate it using IntelliSuite software. Okay, this helps a lot of people. Okay, so the same shape of mask can be sorry, the same profile, if it has to be generated on 111, then a plus mask is not used. Instead, two different rectangles which are meeting at a corner can be used to create this shape. Okay, so here you can see that we are trying to create an octagon shape. Okay, so I'll pause this. You can see 1 2 3 1 2 3 4 5 6 7 8 8 directions. We need to stop this. Okay, we need to stop etching, but sometimes we didn't know how much to etch. Okay, it goes further, and it becomes a hexagon. So as a process engineer, this is what the major problem is. We don't know where to stop the etching. Okay, we just keep it and say 120 minutes of etching, and we will see sometimes some weird profile might have got created. Okay, so these are the things that can be predicted in the software. This saves a lot of time and money. Okay, so similarly, those people who are working with materials other than silicon, like INP is one material, indium phosphide, and those people who are into photonics, people use INP widely. So you can even do process simulation on INP materials also. Okay. So INP material as such is a directional, the orientation is different in different directions. Okay. So whereas in silicon, it is in one particular direction in all sides. Okay, if it is in oriented with x direction, it is x direction alone. But whereas INP material, in different direction, different orientations are there. So same plus mask, when we use, on one side it gives a triangle or a V profile, and another side it gives a different shape altogether. Okay, so these things can be predicted, and these are simulated based on the experimental data. So these results can be reliable. Okay, AT cut and Z cut. Here we have the AT cut and Z cut. Same mask, same etching conditions, but different profiles are generated. Okay, so as academicians, if you are interested to explore more, there are few academic partnerships available. You can visit the website intellisense.com for more details. Okay, so with this, I would like to conclude my talk with the summary. Okay, so what we saw was different types of approaches of designing, and then we had seen some of the research opportunities in MEMS simulation using IntelliSuite software, and process deviation studies in the fabrication process flow, and we also saw some of these bulk micromachining methods also. So if you have any questions, I'll be happy to answer them. So this is what I have for today to showcase it to you. So tomorrow I'll come up with some more examples. We'll see the software directly, how it can be designed, simulated, and different simulations can be available. So anyone having any questions?
Please
Sir,
Unmute
there is a
yourself
one
and ask him.
question. There is a one question in chat box.
Okay, I'll open my chat box. I'll stop sharing my screen and open the chat box.
Shall I read it, sir?
I think, yeah,
Which one is
okay.
good?
Yeah, 1 second. I think, yeah, I'll go to chat box. Yes. Okay, fine. Okay, so I'll come from the beginning. Which is the question here? I'll see.
Sir, which one is good? Top-down design approach or bottom-up design approach?
Yes. Okay, VC Kumar. Okay. So
Yeah.
which one is good? Top-down design approach or bottom-up design approach? Okay, good question. So I would recommend both ways because as a design engineer, when I look at top-down design approach is much easier for you to come up with a design because we don't have to spend too much time in designing a 3D CAD model. Okay, so top-down design approach is much easier. In another way is if you want to simulate it in FEM, you may have to wait for 1 hour, 2 hour, 3 hour kind of simulation. But whereas when you do it from top-down design, you don't have to wait for such a long time. The simulation can be done within less than 5 minutes. Okay, so if you are beginner meaning you don't know your final design, or you are in the process of optimizing it, as a starting point, please use the top down design approach and then come up with an approximate design and then start tuning them. After that you can do a FEM simulation, because FEM simulation are widely accepted. So we also need to see what is the acceptance of Lagrangian model or the element based modeling as compared to FEM model. Most of the researchers compare or look for FEM simulations. Okay, so FEM simulation can be compared with your top down design simulation later. Okay, so as a start you can go to top down design approach, but to showcase and also to benchmark, please do the FEM simulation, that is a 3D CAD model, so that you can compare the two results.
One more
Okay, and
question.
another question is COMSOL multiphysics good for FEM simulation? Well, COMSOL multiphysics has been used by many people. I agree that it is very good for FEM simulation. Yes, it is good for simulation. But what I also have heard from many people is that the process deviation studies cannot be incorporated in COMSOL multiphysics because it does not have process simulation there. Okay. Point two is here it is more of a graphic based design approach and everything is GUI based, so that it's easy to use IntelliSuite rather than the other tool. And third is the convergence issue. The convergence issue is not seen typically in IntelliSuite. Okay, so here we just optimize on the mesh. We see what is the optimized mesh that is required, and we just simulate them. So 99% we don't see a convergence issue at all, which is seen in the other tool. Okay, so that's what my answer to you.
Okay, sir. My
Yeah.
question
Yes.
is what is the price for the institution in your software, sir?
Institution here as audience, are they all from VTU only or outside Karnataka also?
Outside all over India, sir.
All over India. Okay.
Ah.
As such, there is a notification what I saw recently from VTU is that for VTU colleges, IntelliSense had given the software to the VTU colleges in 2006 itself. So they can approach VTU directly, Vishweshwaraya Technological University. I mean, those who are outside Karnataka, I'm telling you what VTU
Okay.
is. Vishweshwaraya Technological University, they can directly write to them and they get the software from them directly. Okay, you don't have to get the you get the tool from us directly. Those who are out of Karnataka, those who are looking at, there are different options of pricing. So based on the module of your choice, the price is decided. So for more details about pricing and other things and university partnership programs and what benefits you get, so everything, please write to this email ID called as india@intellisense.com.
Okay.
Okay, so I'll share the slide. So here, so
Because
I would
many
recommend.
people are doing the research on this one. If they require, if the
Yes.
affordable price, they can buy your software. That's why.
Yeah, I mean, they can discuss directly with our sales team, and then they can get more information.
Okay.
Okay. So is my screen seen?
Yeah, I've seen it.
Yeah. So you can write to us at india@intellisense.com.
Sir, any evaluation version is available? I'm asking
Yes.
for curiosity.
Please go to intellisense.com website and then please fill up the form and then get your evaluation license for 30 days.
Okay. But
Okay.
all features are not available. Only few features are
No.
available.
All features, full features are available, but the license is limited only for 30 days. That's all.
Okay, sir.
Yeah.
I think from this one, the participants can use the intelligence software.
Yes. Go to intellisense.com and then get your 30-day trial.
That's very nice, sir. Any question from the audience?
Yes. Any more questions?
Okay. Okay, Maheshan.
Yes, yes, sir. It's my privilege to thanks Sripada sir for giving a pleasant presentation, and he has given insight of the MEMS technology through the software, and he also told that the evaluation is good for participants to can download and they can check for the evolution version, and they can purchase and they can use it for their research as well as for the students. Thank you, sir. Thank you very much on behalf of Electrical Engineering Department.
Yes.
Personally, thank you, sir.
Yeah. So one last question, what I see is, do you take up manufacturing MEMS sensor? Yes, we do. We have already done a couple of them for academics. So you can write to us for more details. We take up fabrication for low volumes also for academics.
Sir, one more thing, sir.
Yes, please say me. Yes, sir.
Sir, tomorrow's session can be evaluated, show the how to build a periscope step by step, sir. Is possible?
Sure. Okay. I'll take up one device and then show how the electrical modeling and mechanical modeling can be made. And then how do we start in the software? How do we design them?
Sir. Yes, sir.
Then how do we simulate and compare the results?
That's fine, sir.
Yeah. Okay.
Yes, sir.
Sure.
Okay, sir. Thank you, sir.
Thank you.
Okay.
Thank
Tomorrow
you.
afternoon we'll meet at 2:25, sir. Thank you.
Sure. Thank you. Bye.
Thank you, sir. Thank you. Maheshan?
Yes, sir.
Can you end the meeting?
Wait for 5 minutes.
For the filling this one, na? Nageshwar Rao, come to video. Nageshwar Rao, are you there? Nageshwar Rao? Maheshan?
Yes, sir.
Nageshwar is my what? You already know that, na? Is my
Narsrao Pet.
Narsrao Pet, yeah.
He is there in the meeting.
Meeting, but he's not coming to.
Audio is muted. Audio mute ಆಗಿದೆ.
ಮ್ಯೂಟ್ ಆಗಿದೆ. ಓಕೆ. He left, I think. So. He is there. He is there.
He is there. Is next to Maheshan sir. But he is not unmuting. Request ಕಳಿಸ್ತೀನಿ ತಡಿ.
No, he is in Nasrapet. I am in Bangalore.
I'm sending the request.
Mr. Nageshwar Rao.
Hello, can we leave, sir? Can we leave?
Yeah. If you fill the form, you can leave.
Okay, thank you, sir.
Who have completed the feedback form filling, yes, they can leave the meeting. Tomorrow morning we'll meet around 9:55. All participants are request, we coordinators are requesting, tell any improvement is required. Hello, mute yourself, unmute yourself, please give the suggestions. Hello, participants. Hello, please unmute yourself and give any suggestions to improve for tomorrow or day after tomorrow. ಹಲೋ, ಏನಪ್ಪ ಯಾರು ಕೇಳೋದೇ ಇಲ್ಲ ಅಂತಾರಲ್ಲ ಮಹೇಶನ್?
ಇಲ್ಲ ನೀವು ಇದು ಆಗಿದೆ, ಅನ್ಮ್ಯೂಟ್ ಆಗ್ತಿಲ್ಲ ಇಲ್ಲಿ ನೋಡಿ.
ಅನ್ಮ್ಯೂಟ್ ಆಫ್ ಮಾಡಿ ನೀವು.
ನಾನ್ ಮಾಡಿದ್ರೆ ಆಗಲ್ಲ, ಅಲ್ಲಿ ಹೋಸ್ಟ್ ಮಾಡ್ಬೇಕು.
ಸರ್ ನೀವು ಮಾಡಿ.
ಕೊಟ್ಟಿದ್ದೀನಲ್ಲ, ಹಲೋ ಅಟೆಂಡೆನ್ಸ್ ಟು ಅನ್ಮ್ಯೂಟ್ ದೆಮ್ಸೆಲ್ಫ್.
ಓಕೆ, ಆಗಲ್ಲ.
ಆಗ್ತಾ ಇಲ್ವಾ? ನೀವು ಮಾಡಕ್ ಆಗ್ತಾ ಇಲ್ವಾ? ರಿಕ್ವೆಸ್ಟ್ ಸೆಂಟ್ ಅನ್ಮ್ಯೂಟ್ ದೆಮ್ಸೆಲ್ಫ್, ಅನ್ಮ್ಯೂಟ್ ಆಗ್ಬೇಕು. ಅನ್ಮ್ಯೂಟ್ ಆಲ್. ಓಕೆ, ಬರ್ತಾ ಇದೆಯಲ್ಲ ಅಟೆಂಡೆನ್ಸ್ ಗೆ ಅನ್ಮ್ಯೂಟ್ ದೆಮ್ಸೆಲ್ಫ್. ಬರ್ಲಿಲ್ಲ?
ಗುರುಸ್ವಾಮಿ ಇದಾರೆ ನೋಡಿ ಅಲ್ಲಿ.
ಎಲ್ಲಿದ್ದಾರೆ?
ಗುರುಸ್ವಾಮಿ ಇರ್ಬೇಕು.
ಗುರುಸ್ವಾಮಿ, KP ಗುರುಸ್ವಾಮಿ.
KPG ಸರ್ ಬನ್ನಿ.
ಇದಾರೆ,
ಅವರೇ ಅನ್ಮ್ಯೂಟ್ ಆಗ್ಬೇಕಪ್ಪ ಮಹೇಶನ್.
ಹೌದು.
ರಿಕ್ವೆಸ್ಟ್ ಸೆಂಟ್ ಬಟ್ ನೋ ರಿಯಾಕ್ಷನ್. ಫೋನ್ ಇಟ್ಬಿಟ್ಟು ಎಲ್ಲ ಹೋಗ್ಬಿಟ್ಟಿದ್ದಾರೆ.
ಎಕ್ಸಾಮ್ ಇತ್ತ ಇವತ್ತು ಅವ್ರಿಗೆ? ಇಲ್ವಲ್ಲ, ಬೆಳಿಗ್ಗೆ ಇದ್ದಿದ್ದು.
ಇವತ್ತು 7 ಅಲ್ವಾ?
ಜೈಪಾಲ್
ಸರ್ ಹೇಳಿ.
ಹೇಗಿದ್ಯಪ್ಪ?
ಚೆನ್ನಾಗಿದೆ ಸರ್, ಪರವಾಗಿಲ್ಲ.
ಏನಾದ್ರು ಸಜೆಷನ್ಸ್ ಇದೆಯಪ್ಪ ಇಂಪ್ರೂವ್ಮೆಂಟ್ ಗೆ?
ಏನಿಲ್ಲ ಸರ್, ಎಲ್ಲ ಚೆನ್ನಾಗೇ ನಡೀತಿದೆ, ಏನ್ ತೊಂದ್ರೆ ಇಲ್ಲ.
ತೊಂದ್ರೆ ಇಲ್ಲ. ಹೇಗಿದೆ ರಿಸರ್ಚ್ ಸ್ಪೀಕರ್ಸ್ ಎಲ್ಲ ಹೇಗಿದ್ದಾರೆ? ಎಲ್ಲ ಇದಾಗ್ತದ್ಯಾ? ಕ್ಲಿಯರ್ ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ?
ಅರ್ಥ ಆಗ್ತಾ ಇದೆ ಸರ್. ಸ್ವಲ್ಪ ನಂಗೆ ಅಂದ್ರೆ ರಿಲೇಟೆಡ್ ಇಲ್ದೇ ಇರೋದು ಸ್ವಲ್ಪ ಕಷ್ಟ ಆಗ್ತಾ ಇದೆ ಅಷ್ಟೇ.
ಯಾವ್ದು ರಿಲೇಟೆಡ್ ಇಲ್ಲದೆ ಇರೋದು?
ನಿನ್ನೆ ಎಲ್ಲ ಚೆನ್ನಾಗಿದೆ ಸರ್, ನಿನ್ನೆ ತುಂಬಾ ಚೆನ್ನಾಗಿದೆ.
ಇವತ್ತು ರಿಲೇಟೆಡ್ ಇರಲಿಲ್ಲ. ಓಕೆ. ಕಂಟ್ರೋಲ್ ಸಿಸ್ಟಮ್ ಜಾಸ್ತಿ ಇರ್ಲಿಲ್ಲ, ನಾಳೆ ಬರುತ್ತೆ ಕಂಟ್ರೋಲ್ ಸಿಸ್ಟಮ್.
ಅದೇ ನಾಳೆ ಚೆನ್ನಾಗಿದೆ, ನಾಳೆ ನಾಡಿದ್ದು 2 ದಿವಸ ಚೆನ್ನಾಗಿದೆ.
ಎಲ್ಲ ನಾಳೆ ಎಲ್ಲ ಕಂಟ್ರೋಲ್ ಸಿಸ್ಟಮ್ ಇದೆ. ಇಲ್ಲ ಇವತ್ತಿನ ಮಾರ್ನಿಂಗ್ ಸೆಷನ್ ತನಕ ಪೂರ್ತಿ ಇತ್ತು. ಯಾವುದು ಸೆನ್ಸರ್ಸ್ ಮೇಲೆ ಇತ್ತು. ನಾಳೆಯಿಂದ ಇವತ್ತು ಮಧ್ಯಾಹ್ನ ಪ್ಲಾಟೂನ್ ಕಂಟ್ರೋಲ್ ಸಿಸ್ಟಮ್ ಆದ್ಮೇಲೆ ನೆಕ್ಸ್ಟ್ ಇಂದ ನಾಳೆ ತನಕ ಕಂಟ್ರೋಲ್ ಇದೆ ಪೂರ್ತಿ.
ಅದೇ ಸರ್.
Other things are okay.
Yeah, everything is fine, sir. Overall.
All resource speakers audio is audible.
Yes, sir.
Clearly.
Yes, sir. Yes, sir.
No need to any disturbance ಏನು ಬರ್ತಾ ಇಲ್ಲಲ್ಲ?
ಇಲ್ಲ ಸರ್, ಯಾವುದೇ ಬರ್ತಾ ಇಲ್ಲ ಸರ್.
ಬರ್ತಾ ಇಲ್ವಾ?
Yes, sir.
ನವೀನ್ ಅಟೆಂಡ್ ಆಗ್ತಾ ಇದಾರಲ್ಲ?
ನವೀನ್ ಅಟೆಂಡ್ ಆಗ್ತಾ ಇದ್ದಾನೆ ಸರ್.
Okay. Thanks.
Hello, Prasanna sir.
Nageshwar Rao.
Sir, good evening.
Good evening. Tell us to improve anything.
Sir?
Tell us to improve. Any improvement is required?
Nothing, sir. It's fine. But you have not shared the presentations of the resource person, sir.
No, first days I shared. Day 1 I shared yesterday. You have not received?
No, sir. I have not received the mail.
No. I sent to all email address. Your what is registered email address? I sent yesterday.
Okay, sir.
Day 2 tomorrow. Today I am going to send. Like
Okay, fine.
alternative days I am sending.
Okay, sir. Fine.
Apart from that, any improvement is required?
No, sir. Everything is fine.
Fine.
It's going smooth. Fine.
When Nageshwara is there, that should be go smooth only.
Yeah. That's why it is going smooth.
Sir, is it necessary to share it in WhatsApp group? PPTs?
But the what size is big.
Okay.
Even Prashant is telling that his PPT size is 100 MB.
Oh, we cannot share.
He cannot share and also he cannot send. That's why I asked him to make PDF and send. Okay. Anyhow, recording is going on. Every day recording is going on. We'll send the record also.